Hello. So in this video, we're going to start chapter 24, Magnetism. This is the very beginning of the very first part of the chapter 24, Magnetism. Magnetism is actually known for a long, long time, that even in the ancient Greek, people knew that there is some magical or unusual rocks that actually attracts iron bits, right? So it's been a long, people has been known this phenomena for a long time. And magnetic force is very similar to electric force. So you guys, some people do get confused with those two. But similar to electric force, magnetic source of a magnetic force, there are two polarities. Just like for electric force, you have a positive and negative. For magnetic force, there are north pole and a south, north and south. Okay, north seeking pole and then a south seeking pole. Just like electric field, like charges repel, unlike charges attracts. So like poles, like north and north and south and south, they repel, and unlike poles, attracts. Let me show you the demonstration video I did. Let's start with this one. Computer sound here. So here. So Avery, what do you have in your hand again?
Baby oil with some little stuff in it.
The little stuff are iron bits. Can you say?
Iron bits.
Iron bits. And then what's this?
A magnet.
This is bar magnets. All right, let's see. Here we have a white sheet. Can you put the magnet on the white sheet, please? Place it there. Yeah, thank you. Gesundheit,
So when you put this
I'm a little concerned about this, but
this, do you see? There's little iron bits and it looks like hair.
they're making a hair. Yeah, this is so irons without the magnet bars, they're just pieces of iron, but when they're close to the magnetic field, it aligns along the magnetic field, so we see these magnetic field lines. That's why each of iron bits are aligning along the magnetic field. Okay, so those are the, you see those iron bits that making a hair, my daughter calls this a hair, is along with the magnetic field lines. That means that irons are attracted, they feel the magnetic force, magnetic field. But are these irons magnetized? So that will be a question to the next video. But I have another one to show you. Let me see, I'll show you another video. So the like poles, north and north, south and south, magnetic force repels. North and south attracts. So here's the bar magnet, and it has a north and south, two different poles. I have another one here, and like poles repels. They don't like each other, right? North and north. And what happens? Unlike poles, north and south, beep, 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 sticks, attract. Yeah, so that. Let me go into the whiteboard just to summarize all these. It's pretty straightforward. Okay. Okay, so we're in chapter 24, magnetism. Oops, sorry, didn't mean that. Chapter 24, magnetism. There are two poles. North seeking pole and south seeking pole, north and south, which produce, those are the ones that produce magnetic force. They feel the magnetic force. Like poles, like north and north or south and south, the direction of a magnetic force is repel. And unlike poles, attract. So it's very similar, right? You saw the north and north, south and south, but very different from electric charge is that unlike, so here's the important part, unlike electric charge, there is no magnetic monopoles. There is no magnetic monopoles, which means that you never find north seeking pole by itself or south seeking pole by itself. They always come in pair. So always come in pairs. North and south. So what happens? You have a bar magnet like this and north and south, right? And let's say I cut this bar magnet into a half, north and south, smaller and smaller and smaller and smaller. It's always north and south. You're never going to have just the north by itself or south by itself. So that's the very big difference from electric charge. So imagine, remember the dipoles, electric dipoles, where you have the plus and minus, the same charge, but then oppositely charged, and they're separated by the distance d. So magnet acts just like that. Electric dipoles, magnets is a magnetic dipole. It always comes as a two poles, dipoles. And therefore, you can imagine that magnetic field. So you can also draw the magnetic field line, just like electric field lines that we drawn, right? So by having the one magnet, bar magnet, it creates the magnetic field. When you put another magnetic material in it, it feels the force and it's going to move along the magnetic field lines. So we draw the magnetic field line that comes out from North Pole, goes into the South Pole. And as you can see, magnetic field lines is also a vector, just like electric field lines. Magnetic field lines are vectors. And similar, um, very similar to the electric field lines, more number of lines, magnetic field lines. This is the magnetic field lines. Um, per unit volume, per volume. Uh, that means stronger magnetic field. So even though, so magnetic field lines, magnetic. Physicists tends to use B for the magnetic field. I believe engineers use H, uppercase H for magnetic field. It's a vector. Um, so then let me see. So what it means is that, let's say what you saw was we made baby using a baby oil, so the it's not, rather than a water, it's more viscous. Then I put some iron bits inside the baby oil uh, bottle, and those iron bits in it without the magnets. It's just a regular iron bit. It just falls down. It just um, it stays at the bottom of the bottle. However, if I bring magnet next to it, these iron bits does feel, although at that moment it's not magnetized, right? They're not moving, they're not being attracted to each other or repelled each other. They're just regular iron bits. But when they are in a magnetic field, they feel this magnetic field and they feel the magnetic force, and they're going to be aligned along the magnetic field lines. And those are the magnetic field lines that you could see in the video that I just showed you. There's a This is the typical one that I actually show when I'm in the class. We have this tool uh, in the college, so I like to show you this. But since I can't go in, I can't go into the college on campus, so I'll show you this video. Let's see. Okay. Here. Sorry. Okay, so what you've seen was 3D view of a magnetic field. Oops, hold on. Sorry, just had that. YouTube still continue playing. What you've seen was 3D view of a magnetic field produced by the bar magnet that had a north and south. And then as you can imagine that there is a magnetic field line just like similar to those electric dipoles, right? You have a two poles oppositely opposite unlike poles, and then it creates the north poles to the south pole, south seeking pole, and goes into makes that pattern like that. And it is 3D. So irons are aligned along the magnetic field lines. Okay, so that's about it that I want to discuss in this video. And in the next video, we're going to discuss how the iron feels the magnetic field. If iron is not magnetized, or is it magnetized temporarily? So we're going to discuss that in the next video. But for now, I see you in a discussion.